Hi everyone, my name's Alex. I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. Welcome to the fourth and final episode of this video series on welding distortion. In this episode we'll discuss what to do in order to influence welding distortion. And here I deliberately said influence because in case of welding we want to minimize distortion, whereas in case of flame straightening we want to maximize it. This episode's content, however, serves to show you how to minimize distortion. As a guideline for flame straightening, you accordingly have to do the opposite. So, let's take a look. As mentioned in the earlier episodes, welding distortion has more than just one cause. Let's first distinguish the two most relevant causes, and let's term the first one geometrical distortion. It is caused by opening or closing of gaps or by local workpiece buckling between tacks. I'd say that geometrical distortion messes with our workpieces mostly until we have properly finished tacking. From then on, I'd say the second most relevant cause, that is solid body distortion, takes the lead. Solid body distortion is the result of what we called in the earlier episodes the primary mechanism of welding distortion. We already know quite something about solid body distortion. Essential, however, is that we cannot get rid of it because of temperature differences in our workpieces during welding. These drive solid body distortion. But we can diminish it with the strategies that follow. But first, a few words on geometrical distortion. We could narrow this term down to the problem of tacking with gaps and sufficient tacking. The neatest case that will give minimum geometrical distortion is of course a workpiece with zero gap fit up, like here, and little chance of the precuts to move on us as tacking progresses. This is a feature of good workpiece design and good prep work. In reality, however, we typically have to deal with more or less of a gap in the precut assembly, like here. And what happens when we tack with a gap is that, if we tack here, the gap closes a little because the cooling tack contracts, depending on the case, more or less freely. The master anticipates that and positions the precut so that after the tack has contracted, the workpiece geometry is as desired. Of course, that's an eyeballing task, and more commonly welders mechanically clamp or straighten the assembly until tacking has progressed sufficiently. But even without gaps, we have to be careful not to generate geometrical distortion because of gaps that open. Most frequently this happens with the first tack, like in this example here. This face is machined flat and sits on the second precut without a notable gap. And as soon as the first tack has cooled, you see that it contracted quite freely and opened up a gap. This is commonly prevented by either clamping, fixturing, or a neat workpiece design in which the precuts index and lock with each other. As tacking progresses, this becomes less of a problem because the assembly gets more and more rigid. And this brings us to my last remark on geometrical distortion, which is sufficient tacking. The problem of opening gaps is only solved with sufficient tacking. The thinner our wall thicknesses and the more flat the joints are, the more we can observe the tendency of buckling between tacks, like on this 0.6 mm stainless steel sample here. I've marked the tack spacing, which was roughly 100 mm, and you can see nicely how the sheets try to buckle between the tacks. Obviously this is local distortion, but it most probably will cause some overall distortion as well. You also see that the sample tried as a consequence of buckling to keyhole on me, but that's not the point here. Obviously the tack spacing here was insufficient, meaning not close enough. But now let's focus on the much more hazy but interesting topic of solid body distortion. From the findings in the previous episodes, we can derive 3 overall strategies to reduce solid body distortion. These are in order of effectiveness: homogeneous preheating of the workpiece, increasing heated spot flexibility, and reducing heated spot size. But let's focus on these 3 one after the other. The most effective strategy to reduce distortion is homogeneous preheating of the workpiece. This can be done, for example, with heating blankets, with ovens, or simply with the oxyacetylene torch. Preheating effectively reduces temperature differences in the workpiece during welding and thereby reduces plastic strains, which are the cause of distortion. With welding brittle materials, it also reduces the risk of cracking for the same reason. But this effectiveness is only true for a homogeneous preheat. In contrast to that, welders sometimes use local preheat. For example, before welding, they heat this area around here. But the latter is only intended to decrease cooling speed of the weld in order, for example, to keep it from hardening. But back to homogeneous preheat. Homogeneous preheat would be to heat the whole workpiece before welding to an even elevated temperature. We may keep in mind that the higher the preheating temperature, the smaller is solid body distortion. In theory, we can even get rid of distortion if we preheat the workpiece close to melting temperature. By the way, this was historically used to exquisitely weld cast iron, which otherwise may severely suffer from cracking. But of course, there is a natural limit for the preheating temperature. So usually we don't even yet have to worry about surface scaling, for example. The workpiece's mechanical properties should not deteriorate because of preheating. This, however, takes place already when the material begins to recrystallize. That means the thousands and thousands of crystals our polycrystalline workpieces are made of start to grow on us and become larger and larger. Recrystallization occurs at much lower temperatures than the melting temperature and will diminish material strength permanently. Aside from that, allowable preheating temperatures can be limited even more by other processes, like, for example, carbide precipitation, which embrittles many stainless steel alloys. In other cases, homogeneous preheating can be impractical because of workpiece size. Just think of a ship's hull, for example. Or because it's unreasonable for the welder. Think of a workpiece inside of which you have to be for welding. For example, a boiler, a crane chassis, or what have you. So even though preheating may be the most effective strategy to reduce solid body distortion, there are well-defined limits to its application. The second strategy is increasing heated spot flexibility. This one, however, can be difficult to implement on actual workpieces. To highlight what it means, consider these examples. In the first episode, we observed local thickening of these 2 samples due to local heating. The heated spot on this sample was quite distant from the edge, whereas on this sample it was close to the edge. With the latter, we found notably less thickening, which also means notably less distortion. We already know why this is. Here the heated spot's thermal expansion was much less constrained than here. The result was little stresses during heating and therefore little plastic strains. Allowing the heated spot to expand freely in ideally all directions is the essence of the strategy. We can basically implement this by having small welded joints and rather open designs, such as frames in comparison to hulls. Consider this example, where we could increase heated spot flexibility by introducing some cutouts like here. So in this case, these welds would be more free to expand in this direction while they are being hot than before. Also, there are joint types which are less constraining. For example, in this regard, corner joints are better than butt joints. Also, the location of the weld bead in the workpiece can be smart or not so smart in terms of constraining. Or we can implement this strategy by smartly breaking up our welded design into sub-assemblies, which are finish welded before final welding assembly. Obviously, this strategy to reduce welding distortion can only be implemented in the design stage, so it is more of a method for the expert designer than for the welder. The natural limits here are mostly of a manufacturing nature, for example, avoiding notches, accessibility, minimum wall thicknesses, etc. And now at this point we must deduce something very essential, which is often misunderstood. According to the strategy, it's a mistake to clamp, fixture or jig a workpiece other than for tacking. Having it clamped, fixtured or jigged during welding increases the workpiece rigidity and therefore constrains the heated spot expansion more than necessary. This results in more distortion. I know, it sounds unintuitive, and surely welding table manufacturers don't like hearing it. But I will prove this with an experiment at the end of this episode. The third strategy is reducing heated spot size. This, I'd say, is the most frequently used method, even if the two previous ones are more effective. But why reducing heated spot size? Isn't this contrary to the preheating strategy? Well, again, preheating only reduces distortion if it is of a homogeneous nature. Here, we think of the heated spot as having a given higher temperature than the rest of the workpiece. Now think of it from a flame straightening point of view. Larger heated spots led to more deformation than smaller ones. This is because the zones loaded with plastic strain and residual stresses are larger with larger heated spots. So to reduce heated spot size, we obviously should reduce weld bead size as much as possible. Duh! But our workpieces must have a certain strength, so there is a lower limit to reducing weld bead size. But to a certain extent we can also reduce heated spot size for a given weld bead size, like in this example. Let's say this is the size of the heated spot when we conventionally weld this joint, and we can use some certain techniques to reduce the size of this heated spot for a given size of a weld. Process developers and welding equipment manufacturers already did their part in this and established welding techniques with so-called higher energy density. This results in smaller heated spots for a given weld bead size. So in terms of distortion, TIG welding, for example, is better than oxyacetylene welding because the former focuses the heat much more. But this is not the end of the line. Even for a given welding process, say TIG welding for example, there are techniques to reduce the heated spot size. Pulse welding for example. This is a very smart technique which exploits heat conductivity's need for time. By pulse welding, we repeatedly create a melt puddle of given size in a short time span with high current, after which the machine switches to a lower background current, during which we travel the torch. This limits the amount of heat which is naturally carried away by the workpiece to form the heated spot. Of a similar nature in this regard is the old school rule of increasing travel speed, or welding faster if you will. The thought behind it is the same as for pulse welding. As we travel the torch faster over the workpiece, the heated spot at a given location gets less time to grow. Well, and the last method of reducing heated spot size is using heat sinks, typically out of copper or aluminum, placed close to the weld. Even though this might require more welding current, the heated spot size may become smaller since most of the welding heat is conducted into the heatsink. But here we must make sure at the same time not to increase workpiece rigidity with the heatsink, otherwise strategy number 2 is injured. But all these neat methods of reducing heated spot size have a natural limit. The smaller the heated spot, the more intense our workpiece is strained in the heated zone. In engineering terms, the temperature and strain gradients increase. With soft and ductile materials, this may be of no consequence, but the high strength or the brittle materials may suffer from local embrittlement or even from local cracking. You almost made it through this episode's talking part. There is but one sidekick strategy left. It's the method of keeping things symmetrical. This means not just the workpiece geometry, but also means heated spot location and movement during welding. Consider this example here, and let's say that we have to weld this workpiece from both sides. We could do this the conventional way and weld first up here and then down there. But if we want to keep things symmetrical, we could also have two welders weld on the top and bottom side synchronously in a way like this. This way, however, we can only minimize bending or curving distortion. Shortening or shape-changing distortion cannot be avoided this way. In other words, this way we only can keep the workpiece symmetrical. At this point you may say, wait a minute, didn't you forget to mention reducing distortion by coming up with a smart welding sequence? Many welding books advise that. Actually, no. Because a good welding sequence gives low distortion because it implements the 4 previously mentioned strategies more or less simultaneously. This is, for example, because during welding the workpiece gradually heats up, which in turn gradually satisfies strategy number 1. However, at the same time the workpiece may become less flexible for the heated spot expansion, which dissatisfies strategy number 2. Furthermore, at the same time, heat conductivity of the workpiece rises because it gets more and more connected by the welds, which may satisfy strategy number 3 by reducing heated spot size. So, you see, the whole distortional problem can very quickly become very complicated, which might be the reason why so few guidelines are available to help finding a good welding sequence. But don't worry, the pyramids weren't built in one day either. First, they had to get stones. I mean, slaves. Same here. First, we must understand the basic strategies. Then we can implement the one or the other, or even a combination of them, for example by coming up with a smart welding sequence. But now let's proceed to the experiments in order to prove to you that I'm not telling fairy tales here. The following experiments were a little tricky for me to come up with. They look simple, I know, but quite some thought was necessary to keep things comparable. What we'll do is we will lay down one weld bead of given size on each of these samples of square tubing. On each sample we will employ a different welding strategy and then compare the resulting distortions. To ensure comparability, the following procedure is complied with. The tube's weld seams are all kept at the side. The samples are all prepared on the surface grinder so as to have almost perfectly flat and straight top and bottom, as well as to have the same height. This is necessary to allow for a precise measurement of distortion. Weld bead location and target size is marked and equal on all the samples. And welding is done without filler metal to keep the sample cross-sections and therefore stiffnesses as comparable as possible. This of course calls for TIG welding, which I'll do with fixed current, so no foot pedal. Alright, first off let's check if our ground blanks have any bow to it. Indicator is 10 microns per division. That one's good. One should test both sides in order to make sure that the bow is not like so. But you have to believe me, I did that pre-camera. And this is just to show you that, well, they're quite straight. Next sample is going to be with a copper heatsink. The heatsink has a slight bend to it. Hope you can see that. In order to press it onto the sample all the way on the inside when I apply these two clamps here. And this last sample we're going to preheat to somewhere between 200 and 300 degrees Celsius. We're going to evenly preheat it and not just locally preheat it in order to see which effect the preheat has on distortion. I heat it from the inside in order to cover all the four walls, and I judge the temperature by looking at the discoloration, where yellow to blue indicates somewhere between 200 and 300 degrees Celsius. Well, actually blue is about 300 degrees Celsius and yellow is roughly 200 degrees Celsius. And now we do the welding with 70 amps DCEN. So this next sample is clamped down pretty rigidly. I have two clamps over here in order to keep it from bending upward during the welding. And I'll keep it clamped until it's all the way cooled down. Skipped ahead in time. The sample is now completely cold. And now I'm gonna release the clamps. Okay, our samples have cooled in the meantime, and now let's check how much they distorted. Well, here are the results of this comparison. First of all, I tried very hard to keep the weld bead sizes as close to the target size as possible. They are not perfect to the 1/10 of a millimeter, but give me a break. Also check the inside of the tubes to see that penetration is pretty similar on all these samples, which ensures that the weld nugget is also of comparable size. The samples are bolted to the board on this end here, which you can see in the back. And so by just looking down here, you can immediately see the differences in distortion. The height of these plugs here displays this in a magnified way, which shows pretty significant differences. Now, this one sample up here is our reference, since it was welded as normal as TIG welding can be. 80 amps DCEN, which equals 1 amp per thousandth of an inch of wall thickness, giving a fairly comfortable travel speed. So distortion here is scaled to 100%. The second one here shows the effect of increasing travel speed. 160 amps DCEN, which was pretty tough to keep up with. To be honest, I expected more of a difference, but this method surprisingly reduced distortion only for 3%. The third one was welded with a copper heatsink, you can see it sticking out to the left and the right here, and 95 amps DCEN were necessary to get the weld bead wide enough. Distortion reduced some respectable 23%, quite a lot I think. The pulsed current sample is next. I used 105 amps and 0.1 of a second for the on pulse, along with 40 amps and 0.8 of a second for the background pulse. The result is an impressive and almost 30% reduction of distortion. And the least distorted one is the preheated one. With this one, I used a pretty strong preheat of roughly 300 degrees Celsius and 70 amps DCEN. Distortion is almost merely half of the reference sample. So preheating seems to be the most effective method to reduce distortion. However, in this regard, pulse welding, in my opinion, is the most powerful technique because it requires the least amount of extra work with a significant reduction in distortion. But finally, not to forget this sample up here. This one was welded with the same parameters as our reference, but during welding it was clamped to the welding table, about here and there. And this increase of workpiece rigidity caused distortion to increase a staggering 42%. This inversely confirms strategy number 2, which was increasing heated spot flexibility. This finding shows us that welding table, clamps and welding jigs are powerful tools for fit-up and tacking, but typically shouldn't be used during welding. Well, you've reached the end of this video series, that is, unless there is need for a supplemental episode. I hope the experiments and findings I share here shed some light onto the hazy topic of welding distortion. Also, I hope I could answer the one or the other question on this topic which maybe troubled you in the past. Thank you very much for your interest in this video. I appreciate your time. All the best for your welding projects and thank you.